Today we are going to discuss a new idea for the double and triple integrals. So just recall that in the case of single variable integrals, we had this method of changing variables to something, and or I think we also call this method of substitution, correct? So that was an idea to transform a given integral into a simpler one, isn't it? So that we can perform the integration. So same thing is going to be required over here also. In fact, one of the example which we discussed, where we had to compute the surface area, and the double integral was involving a domain which was a disk. Okay, so we could not immediately write that integral in terms of the Fubini theorem, which kind of integrals it allows us to compute. So but some of these domains are so elementary, and we should be able to compute integrals over such domains. So we will try to transform the integral over a region where we can easily compute the or evaluate the integral. Okay, so this is the underlying idea for this change of variable method. And of course, as we are going to deal with 2 and 3 variables, so this will also involve a little bit of geometric features, so we have to be careful. Okay, it may not be as simple or as straightforward as it was in the case of single integrals. Okay, so that is something which you have to, but the idea is to transform a given region into a simpler one, okay, which we know how to handle. Okay, so this is what I have written over here, and let us start with a situation. Suppose that we have this double integral, we are given to evaluate this double integral. So what we need to do is basically we need to transform this. Okay, so we have to first understand, we don't have to do it always. So if the region is such that we are not able to handle it directly, and we see that there is a chance of transforming it into a new one, okay, which can be handled. So all that will come when you practice. So let us see. So we want to transform this into a new integral. Okay, so here you see that the variables are written u and v. So often we will refer to this one as integral in the xy plane, and this one in the uv plane, and then I have used here dA bar. That means there is an area component correspondingly, and this area component need not be the same. Often it is different. Okay, so we will have to work it out given the transformation. This will have the corresponding form. Okay, so what we need to transform this region to another region. Okay, and sometimes these transformations also help us to transform the integrand as well to a simpler function. Okay, so it kind of takes care both the problems with the domain as well as with the integrand, but often our concern will be the domain. Okay, so what we need a transformation which transforms one region into another. So here I am trying to follow the notation of the book. So they consider the transformation from this S to R. Okay, but there's nothing to worry, because this transformation will be such that it inverse also is there. So often you start with R to S and then write the the transformation which I am writing. Okay, so there's absolute, I'm just following the notation, so there's no confusion. So it's precisely the same as in the book. Okay, so you have a domain, let's say in uv plane, and then you consider a transformation to the xy plane. Okay, so what is going to happen, that x and y are going to be functions of u and v. Okay, and now you see that this is a map. The T is a map from R2 to R2. Okay, this is no longer R2 to R. Now we are trying to transform a region from R2 to R2. Okay, so we will have a lot of discussion about functions from R2 to R2 and R3 to R3 in the following lectures. Okay, but here we are just going to use the simple properties. Okay, so essentially what is going to happen, this x variable is going to look like a function of uv. Often we will forget this g, we will write it x as a function of uv, similarly y is a function of u and v. Okay, so this is a transformation which is going to transform this region into a region R. Okay, so in other words, x and y are functions of u and v. Okay, so we we will have to work out according to the problem that what kind of transformation we need. Okay, so there will be some assumptions on the transforms, but right now we are just trying to define the notion. So we have a transformation, and then we will have these things nice in this in the way that we can we can think of their partial derivatives and so on. So think of this x as a function of u and v, similarly y as a function of u and v, and define the Jacobian of this transformation by this. So the notation is j of u and v, or this partial x and y by partial u and v. So you should not get confused that this is a new partial derivative. No, it is just a notation for the Jacobian, and this is basically defined via this determinant. Okay, so compute the partial derivatives of x with respect to both the variables, similarly by put them in the columns and then compute. This is what it is. Okay, so in a way here I am not writing that x and y have first order partial derivative. So this is assumed when I am talking about the Jacobian. Okay, so the assumptions are when we are trying to do it for integrals, a change of variable, that we assume that the the transformation is invertible. Okay, this is very natural, it's not anything artificial, because if two things are being mapped to one, that means domain will will not have one corresponding. So domain will shrink or it can become completely different, because when we are taking the integration, integration is like summing things up. So if we collapse a lot of things to one thing, that means we are losing in the integration, because if several things I assume to be one, then when I sum them up, on this side I will have only one term, on the other side I have a lot of other terms. Okay, so this is natural to have the one correspondence between both the domains. Okay, so this is the idea that T is invertible. So that means that T inverse exists, and we will assume that these functions g and h, or x and y as functions of u and v, they have first order partial derivatives, because we have to perform integration. So we need to assume that the derivatives, and not only they exist, they are also continuous functions. Okay, yeah, so this is small typo here, this should be comma, and the Jacobian is non-zero. Okay, so the double integral for the so the change of variable formula for the double integrals, it looks like this. So what we were given to evaluate this integral, and we consider this change of variable x as a function of u and v, and y as a function of u and v. So we perform this transformation. So the new domain becomes S, and the function is now going to be a function of u and v, and you have the modulus of the Jacobian, so that modulus of that determinant. So this is basically the area component, which I had written as dA bar. Okay, and in terms of the transformation, you can write it like f of t, because this is nothing but t of u v, and this S is nothing but, because the the t was from S to R, so this is precisely the t inverse of R. Okay, so this is the change of variable formula for the double integral. You might be wondering, like how does one get this? It looks artificial. So what I will do is I will try to give you a sketch of the proof, and the idea is very simple. We have actually talked about this idea earlier also, so I will not write the complete details, but you are welcome to discuss this thing in the office hour. Okay, whenever, if you like. In fact, you can complete when I talk about the idea of the proof. Okay, so I will just give a very brief and vague idea. So you see, we are trying to transform this integral into a new integral, correct? This is what the thing is under this transformation. So all we need to do is we need to see that how does the area component change. Okay, this dA. So if you go back to the definition of double integral, the area component was basically when we were trying to decompose the region into smaller rectangles, and then this was coming out to be dx dy and so on, correct? So we need to basically see the same thing. Okay, if we can figure out that when I decompose one domain into smaller rectangles, how does the small rectangle transform into the new domain, and how does the area change? Once I have that, then I am done, isn't it? So this is what I have written here. Okay, so we need to see that if I divide this into smaller rectangles, okay, so the area is this. So how does this area of small rectangle change under the given transformation? That is what is going to decide that this side what we were going to get, because this is just changing the coordinates. Okay, the main thing is that how does the area component come over here, like how does the Jacobian come over here, isn't it? So we basically yeah, just there's a picture here, so this is easy to, so we look at the image of this. So this is going to go to some part of this thing, and then we try to see that what happens to this new area. Okay, how does it look, can be computed. So this is precisely the idea which involves, you know, the tangent lines, if you remember. So we when we tried to do the double integral, there also we did it. So basically you take a point here and then look at the corresponding images, and then try to so this patch, which is the image of this small rectangle, will be approximated by this parallelogram. Okay, so basically you look at the tangent lines, and then the area of this parallelogram is basically approximated by I mean, this gives you an approximation of the area of the image of this small rectangle. So this is the underlying idea, that's all. And when you compute that, when you write down both the tangents, compute their cross product, you will see that you precisely get this Jacobian term. Okay, so I mean, I'm not going into the details. As I said, you can discuss this in the office hour, but this is precisely the idea. Like, you look at a point here and then try to see this patch on the corresponding domain in the other plane, and see that this area is approximated by just this parallelogram. That's all. Okay, and all you need to write is what is the area of this parallelogram. Okay, this picture is drawn here. So look at these tangent, and this is going to give you an approximation. And once the approximation is there, and then you just have to write down the limit. Okay, so this this formula for double integral, as I just kind of convinced you that it is going to transform via this rule. And you know, the same idea can be carried forward to the case of triple integrals. Okay, now in that case you are going to have functions from R3 to R3. So the transformation is going to take a region from u, v and w plane to a region in x, y and, I should not say plane, I should call it space, x, y and x, y, z space. Okay, so again the same situation, you take an invertible transformation which maps this S from this space to another region R, and this is going to look like this. Now, you know, x, y and z, they are going to be functions of 3 variables, isn't it? So we further assume that these functions are continuous, I mean have continuous first order partial derivatives, and the Jacobian does not vanish. And then we can write down the similar change of variable formula for triple integrals. This is precisely the analog of what we just, you know, I did not write here as x a function of u, v and w and so on. I rather wrote this t, okay, because you know it doesn't fit in this space. So so basically what you need to understand, you need to I mean, depending on the problem, you need to find out what transformation is going to work for us, and then compute its Jacobian and find the how does the region R gets transformed under this T inverse, correct? This is basically T inverse of R, and just compute the integral. Okay, and the often the idea will be to transform a region into a nice rectangle, or you know, a box, or something which fits between two surfaces, you know, in case of triple integral, and in case of double integral which fits into two curves, within the two curves and so on. Okay, so that the Fubini theorem we can apply. So let us, you know, look at some examples. So we are going to discuss a lot of examples, and there are certain examples which are kind of prototype. Okay, and most of these things you will be aware of already. So like the polar coordinates. Okay, so this is a situation which we had an example for in the previous lecture, when we had a domain where we needed to compute the double integral over a disk. Okay, so you know that in R2 we can have this polar coordinates for points, isn't it? So in Cartesian coordinates, what we do, so let us take a point P. We basically reach this point by following the horizontal and vertical lines, correct? So we move x and then y, so we move only horizontally and vertically. Okay, so in the polar coordinates what we do, this is a different way of looking at the point, okay, or a different representation of the point. So basically, you know, the change of variable idea is just it's a change of reference, you know. This is what we are doing. So we try to change the reference points and the reference, so that things look simpler for the integral. Okay, so what we do instead, we look at this point and look at this point in terms of its distance from the origin. Okay, so there's going to be this distance as a variable, and the other variable is like what is the angle from with the x-axis of this line. So this is again a way to you know determine this or represent this point. Okay, so this is called the polar coordinates of the point. So the distance is written as r and the angle is written as theta, and you can see that the theta is going to go from all the way from 0 to 2 pi, and then r is going to be always non-negative, correct? So this is another way of representing a given point in the plane. Okay, we had one as the Cartesian, and then other way is basically involving the distance and the angle with the x-axis. Okay, so this is a different point of view, a different frame of reference to you know represent the points. Okay, but it helps. Okay, so you see that if I have a circle of radius r, the first coordinate, the r, is going to be same. Okay, only the angle will vary from 0 to 2 pi. Okay, so this is how we are going to now look at. And you know, origin is always written as 0 0, so the distance is 0, and then so this is I mean a notation which you should always follow. And often you will see that this is also called a pole. Okay, and this is called the polar coordinates. So polar coordinates, the radius and the angle. Okay, and this will you can easily figure out, because just looking at this is r, this is theta, this is a right angle. So x and y can be written as you know functions of r and theta. So precisely x is r cos theta and y is r sin theta. So u and v here are basically r and theta. Okay, so because this is a standard notation, we don't want to write as u cos v, you know, otherwise that will look bit different. So x and y, I can write them down in terms of the new variables r and theta, and this is precisely the transformation which is you know which we were looking at. And you should try to find the inverse of this transformation, in the sense that you try to write down r and theta in terms of x and y. Okay, there is a word of caution here. This arc10, you know, you have to be a bit careful, because you know depending on the which coordinate which quadrant you are, you have to adjust the theta carefully. Okay, because tan inverse you know is from minus pi by 2 to pi by 2, and so you have to be a little bit careful. But you know, these are the things which you already know. I am not going into the details. So the idea is that you need to find a transformation, and then it's Jacobian. So you compute these terms, and in this case this is precisely just r, the theta term just vanished, because this is cos square plus sin square. Okay, so what does it tell us? It tells us that if I have this integral, okay, this is precisely the integral which we were trying to compute in the previous lecture. So we were trying to find the area of the part of this paraboloid which lies under the plane. Okay, so and we had this double integral to compute to find this area, correct? This is the surface area, and the disk D here is this disk, because it was, you know, bounded above by z equal to 9 plane. So when we look at its projection on the xy plane, it was the disk with this. Okay, so yeah, so I think I should have written here square root, isn't it? Because z is equal to this. So yeah, but you know, these things you can verify. So now look at the change of variable. X equal to r cos theta and y equal to r sin theta. So r is varying from 0 to 3, Okay, this is actually, this is r square in terms of, if you look at here, this is r square. So I should have written here the square root. Okay, but that you can correct it. So r is varying between 0 to 3, and theta is varying because this is a disk, full disk. So theta is varying all the way from 0 to 2 pi. All right. So the reason you are going to get is, now this is a rectangle oops, there is a typo here. This is not 2 commas, 1 comma. So in the r and theta, this is a rectangle. Okay, this is very nice domain. So if I perform this change of variable, compute these partial derivatives, and you will get that the partial derivatives are this, and then just put them in the, substitute them in the formula. So the r transform r is this rectangle here, and you just simplify it. This is going to look like 1 plus 4, and then again cosine square plus sine square will become 1. So this is 4r square, and this r extra term is coming from the Jacobian of the transformation. Okay, and then dr d theta. Now you see, this is such a simple integral. You have something 1 plus 4r square inside a square root, but there is an extra r here. So do a change of variable for single integral, which is with respect to r, and there is nothing in terms of theta here. This is just the integral of a constant function with respect to theta. So compute this, okay, and then verify that this is the answer. So what I am trying to say here, that the disk, where is it? Yeah, the projection of this, which is the disk, is now transformed into a rectangle. Okay, so this is a very easy thing to do, because rectangle when I have, I can apply the Fubini theorem and then just compute the integral. Okay, so this is a very standard change of variable, change the Cartesian coordinates to the polar coordinates. So this is an idea which is helpful when you have these domains which are disk or annular regions. Okay, because there is symmetry around the origin basically. So in such cases, writing down the things in terms of the radius and the angle makes it easier. Okay, so this is and then the other thing is, now this is called the cylindrical coordinates. I think these things you already know, but let me just give you details, so that in case some of you have forgotten. Okay, so the idea is that in R3, again we have the coordinate, the Cartesian coordinates x, y and z, but there are different point of views. First one is the cylindrical coordinates. Okay, so basically what we can do is, if I take a point P in the x, y, z space in R3, or then what we can do is, we can represent this point in terms of r, theta and z. Okay, I'll tell you what is r, theta and z. So I will just talk about looking at this picture, the same thing I have written upstairs. So you have a point. Now we are given this point. So what we do is, we look at its projection in the xy plane. Okay, so once I have a point x, y, z, then the point x, y, 0 is a point in the xyz plane. So sorry, xy plane, isn't it? So if I have a point in the xy plane, I can write down its polar coordinates. Okay, so x, y, 0 I can write down as r, theta, and then 0 is 0. Okay, so basically you have this point. Just think of x, y, and then write it in terms of the distance from the origin, and then the angle it makes with the positive x-axis. Okay, now for the z coordinate, what I do, I just reach the z going vertically. Okay, so I have basically, so this is a point of view where I am trying to locate the x, y in the plane using the polar coordinates, and then z basically as it is. So you see that if I look at this whole thing, the base is going to be of radius, a circle of radius r, and this is basically z. So if you go around, you are going to get like a cylinder, isn't it? So it is going to map all these things, and this is why it is called a cylindrical coordinate system. Okay, and it's very easy, because I know already the polar coordinates are will give you these transformations. that x is r cos theta and y is r sin theta, and z is precisely the same. Okay, so this new coordinates. Okay, now the variables here are going to be r, theta and z. Okay, so the functions are x equal to r cos theta, y equal to r sin theta, and z equal to z, isn't it? So this is a new way of representing the given point. Okay, so this involves the distance, okay, not of the point but it's of its projection from the origin. Okay, and then the angle in the xy plane and the z component. Okay, so this is another way of representing a given point, and it is called the because you can figure out what is the shape here coming out. So this is called the cylindrical coordinates or cylindrical coordinate system. Okay, and this is idea which will help you when the domains are part of the cylinders and so on. Okay, and then we can transform them into nice domains. Okay, and for this transformation you can compute the Jacobian. Okay, for three variables the Jacobian is the determinant of 3 cross 3. So you just compute this thing, and I have an example here from this book. So suppose that this is an integral which we want to compute. Okay, so if you see here, what is this? The z is varying from z equal to square root of x square plus y square to 2. Okay, so this is going to look like, can you guess? Okay, I have a picture. So this is going to look like this. Okay, so there is a z equal to 2 thing, and then x square root of x square plus y square. So this is precisely going to look like a cone type of shape, and the domain here in the xy plane is basically the projection, and then the z is varying from this to this. Okay, so this is precisely a triple integral which lies between two surfaces. One surface is this, other surface is this, and the domain in the xy plane is a disk. Okay, so the disk already suggests that we need to think of polar coordinates. Okay, so when we do that, but then there is another thing which is z here. So this it becomes a cylindrical coordinate system. Okay, so we change to the cylindrical coordinate system, and all you have to do is find the the limits. So limits are very easy because x and y, this is a full disk of radius 2. So the limits for, okay, let me first talk about the limits for z. The limits for z are from this to this, which is given, and this is nothing but r. Okay, so the limit of z is r to 2, and the limits of r, you look at this disk, this is going from 0 to 2, and then theta is going from all the way from 0 to 2 pi. So this is what it is, and now this is just a box in this new variables, isn't it? This is 0 to 2 pi, 0 to 2, and then it's not really a box because there is a r term here. So this is a rectangle, and then the z is varying just a very nice function, z equal to r. Okay, so this is easy to compute, and again this r is coming because of the Jacobian. Okay, the r square is from the integrand. Yeah, this is precisely r square, isn't it? X square plus y square. So if you try to do it, this integral just for x, y and z without making any change, then you will have to do a lot of work, but going to the cylindrical coordinates here makes it so easy. Okay, so this is this is what we have to do. We have to simplify the situation and compute it. Okay, so I am not writing the complete details, but when you are solving these things in the exam, you must write all the details, all the steps. Okay, so I always write verify the answer. I may make a mistake here. And the another useful frame of reference is through this spherical coordinates also. So there is another way of representing a point in R3. See, again I am just kind of repeating this because some of you may have forgotten these things. So again I will just talk about from the picture. So you have a point, and what we can actually do is we can express or represent this point in terms of new coordinates, which are written as rho, theta and phi. Okay, so as this picture says that I started with a point P in this space. Now look at this. So this point, you draw a line to the origin. Okay, so this is going to give me the distance of this point from the origin, which is written as rho. Okay, so this distance is rho, and for any point you know that the distance is unique. Okay, so other thing is this theta. So what is theta? Theta, what you do is you look at the projection of this point again in the xy plane. So you write down the polar coordinates for this. So this r is now a new thing. Okay, this r is the distance as in the previous case also, from the origin to the projection of the point P. So this is basically the distance of the point P prime, which is written over here, to the origin, and theta is the same angle as we had earlier. So the limits for r, in terms of only x and y here. Okay, and then the rho is going to give you because this is the distance, so you can write down rho is going to be precisely square root of x square plus y square plus z square, isn't it? And this one more thing, this will completely determine the point. Okay, this is the angle that this line segment OP makes with the positive z axis. Okay, so you imagine a point and then first look at its distance, and then this angle theta in the xy plane, and then another angle with the, so this is a way to kind of determine, if I give you these three components, the rho, theta and phi, you can completely determine the point. Okay, and vice versa. So this is another way of representing a point in the space. And you notice here that the theta is going to go full circle, so this is going to vary from 0 to 2 pi, and whereas the phi will vary from only from 0 to pi, because this is with the positive z axis, this is the angle of this OP. Okay, so this will go from 0 to pi. All right, and what we have to do is we also have to see that this r can be written in terms of rho, because I mean we are supposed to have a representation of the P in terms of these three coordinates, but right now this x and y are being written as r and theta. So just look at these triangles. Okay, this is a right angle over here, and similarly this is a right angle over here. So I can write this r in terms of rho and the angle. This is phi, this is phi, this is phi, isn't it? So just do that. Okay, so just look at this picture. This x is r cos theta as earlier, and y is r sin theta, and yeah, and just a second. So now, as I said, this r you try to write in terms of these rho and phi. So from this picture you can immediately see that rho is sin phi, isn't it? R is equal to rho sin phi. So this is I mean, you can look at this picture. This is a right angle, this is rho, this is phi. So r is going to be sin phi of sine of this angle, and then this rho. This is just the triangle rule, I mean nothing new. And so basically you just substitute back the value of r in over here. So x is this, y is this, and z, what is z? Again you can check from here. This is a right angle, so z you can express in terms of rho cosine of phi, isn't it? This z is precisely this rho and cosine of this phi. So this is what I have for z. So now you see that I have got a transformation which sends this x via this rule, y via this rule, and z via this rule, and this gives me precisely a new way of looking at the points. Okay, and rho is this because this is just the distance from the origin to the point P. Okay, and one can compute the Jacobian here. Okay, so I have just written the first step over here, and it is going to involve a lot of terms. So you have to find the Jacobian here, and it should come out to be this. Okay, so please verify this. Okay, so what is the advantage here? The advantage here that when I have something which is looking like a sphere, because you see this radial component, this is going to be same on the whole sphere of radius r, or sorry, I should not say r, it's rho. Okay, so when a domain has a symmetry around a point which is origin over here, then this is going to help. Okay, so let us look at an example over here. So suppose that we have to integrate this function over ball. Okay, now you see here the ball is not something which we can immediately apply the Fubini theorem to, and also the function is bit complicated here. If I have to integrate exponential which involves functions of x square, y square and z square, and then there is a power 3 by 2, it's going to be hard. Okay, so rather if I think of this as my rho, okay, which is the same as saying that I am going to look at the spherical coordinates, then things are going to simplify a lot. Okay, so this ball will transform into a box, because everything, the rho, the theta and the phi, they are going to vary between two numbers, and then this function also simplifies here, because this becomes e to the power rho cube, and the Jacobian is going to give you this extra term. So there is a power 3 here and there is a square here, so you can do a small change of variable again for the rho integral, and you get this answer. So these are the things which make a given integral over some domain which we are not able to handle immediately, and it the change of this suitable change of variable makes it into a known type of domain, and then integral can be performed in an easy way. Okay, so this is what I have written, that oops, this I should have said rho cube as I was saying. So you assume that rho cube is t, otherwise you will need one more change of variable. Okay, so you do it in one go, so this should be 3. All right, yeah, I mean these integrals I will not write down the details all these steps, because you can do them better. Okay, now so these were the situations which are special cases of change of variables, but they are so useful that they have their own names, they are different frames of reference. Okay, and they are useful in many other situations. So we will always have these. So when I say spherical coordinates, you have to imagine this picture, and then find the corresponding the transformation over here. Okay, and as I said, whenever you have these kind of terms, x square plus y square plus z square, then try to see that spherical coordinates are going to help you. Okay, now I just finally I give you one more example. Okay, so this is for double integral. Okay, this is now no longer a disk or a ball. Okay, but it's again just a combination of lines. So suppose I have a trapezoidal with vertices at these points. Better to look at this picture. Okay, so suppose this is our domain of integration, and then we want to integrate out just very nice simple function x plus y. Okay, but the domain is this. So you see here there's a small bit of problem. Okay, see, it's not a complicated domain. Okay, our Fubini theorem says that if it was between two lines, we could have done that, but these lines are tilted, and this is not precisely between the two lines, it's combination of two lines here and combination of two lines over here. Okay, but simple mindedly we think about it, if somehow we can rotate this so that these lines become parallel to the coordinate axis, then this transforms into a rectangle, isn't it? And then we can just compute it using the Fubini theorem. So these are very simple ideas, and all we have to do is just try to find the transformation. Okay, so first of all you write down what is this trapezoidal. So when I see, that means you need to write down the sides. Okay, so you can easily compute the equations of the sides, because these are the lines between these 2 points, and then between these 2 points, and so on, isn't it? So you compute, and then you try to figure out that, okay, if I want to send this line, you know, to either to this line or to this line, what will be the transformation? Okay, that's it. So you know, little bit of guesswork sometimes, and sometimes little bit of work on paper you have to do. So in particular, in this case, you consider this transformation, so you have to come up with this. I am not going to have you know, a way of doing it, because a line is given. All I want to do is I want to, you know, take it to the coordinate axis. Okay, so that you should be able to do it. Okay, sometimes it may not be a line, sometimes it could be you know, a curve, and then we want to transform it accordingly. Okay, so if I use this change of variable, so you see that x is a function of u and b, similarly y is a function of u and b, and since we were transforming line to another line, so you see that there are going to be no squares or cube terms, only the linear terms are going to be involved. And you will see that the limits of u and b are going to be this. Okay, and this region over here is, under this transformation, actually transforms into a rectangle. Okay, so the integral now becomes an integral over the rectangle, and then you put x equal to this thing and y equal to this thing, and one term actually gets cancelled, and the Jacobian here is minus 12, by the way, but this is the area component. So you see we had a modulus, because you know, negative terms are not considered in the area, so the area component, the Jacobian is in the area component, so this has to be modulus of this minus 12. So that is why this 12, and this is such a simple integral to compute. Okay, so you think of, you know, several situations of double integrals and triple integrals where making a small change of variable helps. Okay, so there will be a lot of other examples we will give you so that you can practice. Okay, all right.